In this video, I will go through the solutions to the 4 additional examples that we'd set, and then we're going to look at the past paper questions, and I'll work through one with you and show you how to do it. I'll then ask you to work through the second example, and I'll keep showing you the solutions as we go along, but I will be encouraging you to have a go at it, and then I'll leave you the next 3 to try for next week. So first of all, the additional examples. So the first additional example we'd given you was this: what mass of sulfur dioxide can be produced from 1.6 gram of sulfur? And you remember the first thing that we always do is we look for our ratios. So our ratios in this case, 1 to 1 to 1. So 1 sulfur combines with 1 oxygen to produce 1 sulfur dioxide. Number of moles. So read the question carefully. We've got 1.6 grams of sulfur, and we're asked what mass of sulfur dioxide. So we're going to go between these two columns. So we're going to work out the number of moles of sulfur. We're going to produce or work out how much sulfur dioxide has been produced. So number of moles of sulfur, 1.6 grams. The mass of 1 mole of sulfur is 32. We get that from our periodic table above sulfur in the periodic table. So 0.05 mole. So 1.6 over 32, 0.05 mole. Then we use our ratio. So our ratio going between this column and this column is 1 to 1. So what that means is 0.05 mole of sulfur reacts to produce, that should read reacts to produce 0.05 mole of sulfur dioxide, 0.05 mole of SO2. And then the mass, well, we know that 1 mole of SO2, by totaling up the formula, get the RFM, 32 plus 16 times 2 is 64. So we know 1 mole is 64, and then 0.05, well, multiply our 64 by 0.05, and that'll give us 3.2 grams. So our answer is 3.2 grams. Question 2 is done in a similar way. So our ratios, and again we can see no numbers in front of these to get the equation balanced. So 1 to 1 to 1 to 1. In our question, we have 6.5 grams of zinc reacting with sulfuric acid, and you're asked what mass of zinc sulfate can be made. So we're going between the two highlighted columns there, from zinc across to zinc sulfate. Now we've got 6.5 grams of zinc, so we're going to work out this first. So N equals M over RFM. So 6.5, look up zinc in the periodic table, 65 is above it, so 0.1 mole. We're going to go across to the zinc sulfate. Our question asks the mass of zinc sulfate. So 1 to 1 ratio. So therefore 0.1 mole of zinc produces 0.1 mole of zinc sulfate. We know by totaling it up that 1 mole of zinc sulfate, 65 Zn plus 32 S plus 16 times 4 oxygens is 161. So 1 mole of zinc sulfate is 161. So 0.1 mole is going to be 161 times 0.1. And that gives us 16.1 grams. Question 3. Now this is one where our ratios aren't 1 to 1. So 4Na plus O2 gives us 2Na2O. So our ratio is for every 4 sodium atoms, you react with 1 oxygen molecule, and that produces 2 sodium oxide molecules, Na2Os. So what have we got? We're asked what mass of sodium oxide. So we're going to be working out the mass of this from 1.6 grams of oxygen. So we're going to go between these two columns. Now we've got that there's 1.6 grams of oxygen. So let's start off here. N equals M over RFM. So 1.6 O2, 16 times 2 is 32. So the mass of 1 mole is 32. So that gives us 0.05 mole. We're going to go from oxygen to sodium oxide. We're asked in the question what mass of sodium oxide is produced. So 1 to 2 ratio. So for every 1 O2 we make 2 Na2O, so 1 to 2 ratio. So therefore we've worked out here 0.05 mole. So 0.05 mole of oxygen produces 0.05 times 2, and that works out to be 0.1 mole of sodium oxide. So that tells us that's the moles of sodium oxide we've got. And then finally, to get the mass of that, well, again, we go up to our formula, Na2O, 23 times 2 plus 16 is 62. And we know that 1 mole of sodium oxide is 62. and therefore 0.1 mole is going to be 0.1 times 62, 6.2 grams. Our answer is 6.2 grams. And the final one from the additional examples, what mass of sodium oxide is produced from 2.875 grams of sodium. So again, our ratios 4 to 1 to 2, so exactly the same as on the last question. This time we're asked the mass of sodium oxide produced, but we're given the amount of sodium. So this time we're going between these two columns. So we're going to work out the number of moles of sodium. We've got information there to work out the number of moles of sodium. And we know that N equals M over RFM. So 2.875 grams of sodium. 23 is above sodium in the periodic table. So 0.125 mole, which is 1/8 of a mole. Then this time we're scaling between this one and this one. So 4 to 2 ratio. So 4 to 2 ratio. So for every 4 sodium, we produce 2 sodium oxide. Now, most of you will straight away see that's more simplified down to 2 to 1. So for every 2 sodium, we'd make 1 oxygen. So what that means is whatever we've got moles of sodium, we have to divide that by 2. So 2 sodium goes to 1 sodium oxide, 4 would go to 2, 8 would go to 4. That's what a 2 to 1 ratio is. So therefore, what we do is we halve the number of moles. 0.0125 mole is going to produce 0.125 divided by 2. 0.125 divided by 2. And when we put that in, that's 0.0625 moles of sodium oxide. And then finally, to get the mass, so again, same as we saw the last question, the mass of 1 mole of sodium oxide is 62. So 1 mole of sodium oxide 62. So therefore 0.0625 times 62 equals 3.875 grams. Okay, so the last parts of the booklet are just the way these past paper questions come up. Now, what we've done in the last worked examples and so on are exactly the way that we do the questions. But what they've tried to do with these GCSE questions is they try to guide you through the calculation rather than just giving you a blank page and then putting the question up at the top and then just leaving it all for you to do. What they do is they guide you through it. So you'll see if you look at this first question, what they have here is they've got the equation given to you. So they quite often give it because they're more interested in seeing how you do your mole calculations than getting your balanced equation. So there's our equation there, and we'll come to the ratios and so on in a moment. And then if you look at what they do is they ask you to work out relative formula masses. So sometimes what they'll do is they'll ask you to work out one relative formula mass and then turn it into a number of moles. And other times what they'll do is they'll ask you to work out all the relative formula mass. So this one here is ask you to work out the relative formula mass of sodium hydrogen carbonate and sodium carbonate here at the start. And you're going to see that we're going to use those in the question. Then you'll have a number of moles to work out. So they'll ask you a number of moles. And then if you glance down the page, I've just this top half on my slide here at the moment, you'll see that the next thing then says work out from the moles of sodium hydrogen carbonate how much sodium carbonate. So that's our calculation where we scale across the equation. And then they'll finally ask you to work out the mass. So quite often a few relative formula masses at the start, work out a number of moles, scale across the equation, and then work out the mass. So if you go back, it's exactly what we've been doing, right? You'll be looking at the ratios. You'll be asked to work out relative formula masses the way that we have here. You'll be asked to turn that into a number of moles, then scale across the equation, and then turn it into a mass. So it's the 4 steps basically that we've talked about, but they will tell you what to do as you go down the page. So let's do the first one here. So read the question. It says, when sodium hydrogen carbonate, so that's it there, NaHCO3, is heated, it decomposes to form sodium carbonate, water, and carbon dioxide, as shown in the equation below. And there's our products there. And it then says to calculate the relative formula mass of sodium hydrogen carbonate, calculate the relative formula mass of sodium carbonate. So we'll look at the equation first, as we've always done. So if you look at it, you'll see that there's a 2 in front of the NaHCO3. So when we work out the number of moles of that, for every 2 moles of this, we'll make 1 mole of this. That's what's going to be in the question. You'll see that they've asked sodium hydrogen carbonate and sodium carbonate, so that's what's in the question. And as we've done before, we've just put those other ratios on there just in case some of those come up. So let's work out the relative formula mass of sodium hydrogen carbonate. So we know that NaHCO3, so sodium's 23, hydrogen's 1, carbon's 12, oxygen's 16 multiplied by 3, 84. And there we're given 1 mark for that. Then calculate the relative formula mass of Na2CO3. So this time sodium is 23 multiplied by 2, carbon's 12, oxygen 16 multiplied by 3, 106. So the first two parts are fairly straightforward once you've seen the formula for the substance. Now this next one then asks you to work out the number of moles in 8.4 grams of sodium hydrogen carbonate. So it's going to be this one here. Now we've already worked out here that 1 mole is 84. So let's use that. Right? That's the mass of 1 mole. So we know that N, number of moles, is mass that we're given, 8.4 over RFM, this 84. So let's put that in. 8.4 over 84, 0.1 moles. So you'll see the first 3 parts they've guided you through. They've got you to work out the equation has told you the ratios. They've got you to work out the relative formula masses. And there we've got the number of mole. Now, when we come to the next part, it then says how many moles of sodium carbonate can be produced from this 8.4 grams of sodium hydrogen carbonate. Now, I've put back up on the screen, you have it at the top of your page, there's our ratios. So we'd worked out already that we had 0.1 mole of this. So we'd already worked out that there was 0.1 mole of this. And what it's saying is, if you've got 0.1 mole of this, how many moles of this can you produce? Well, that's where we use our ratio. And our ratio, as you can see there, is 2 to 1. So our ratio of NaHCO3 to sodium carbonate 2 to 1. So that means if we've got 0.1 mole, if we're going from 2 to 1, so from 8 to 4, 16 to 8, 32 to 16, we're halving it each time. So what we do is 0.1 over 2, which is 0.05 mole of this. So 2 to 1 ratio, divide that by 2, 0.05 mole of sodium carbonate. And there's our next mark. And then finally, what it asks you to do is calculate the mass of sodium carbonate. So we know from up here that there's 0.05 mole of sodium carbonate. We know from our calculation up at the top that 1 mole of sodium carbonate weighs 106. So 1 mole of sodium carbonate, 106. So to work out the mass, multiply this number of moles, 0.05, by 106, and the answer is 5.3 grams. And what we've done there is excuse me, in a slightly different way, is we've worked out exactly the same way that we've done our calculation before. Now, part F, there's a little bit of a typing error from your notes. Your notes, I think, says something about sodium hydrogen carbonate down here. So your part F should read, when the reaction was carried out, 3.2 grams of sodium carbonate were produced. So that wee bit there is different from your notes, so if you can change it. And what it then says is, what's the percentage yield? Now, do you remember a couple of lessons ago we looked at percentage yield? And what we found is that the percentage yield was the actual yield. So they've told you here 3.2, that's the actual yield. You've worked out from this one that you should have got 5.3 grams. So we've got 3.2, we should have got 5.3. So we do, to work out the percentage of these, 3.2 divided by 5.3, and then make it a percentage, multiplied by 100. And if you put that into your calculator, 60.4%. And then the final part says, give one reason why the percentage yield is lower than 100%. Now, if you go back, I think it's somewhere around page 16 in your notes. Do you remember when we looked at percentage yield, we had this at the top, and I got you to highlight this up. There's the 3 reasons that you don't get 100% of a yield. Do you remember there's loss during transfer? There's side reactions where your reactants can turn into substances that are different from the ones that you want to obtain. And then you remember there's this theoretical thing called equilibrium where the reaction is reversible and doesn't go to completion. So some of your reactants turn into products, but some go back into products. So going back here, one reason, well, any of those 3. So you could say loss during transfer from one container to another. So when you're doing the reaction, you transfer from one container to another. Or you could say that sodium hydrogen carbonate was converted into something different than sodium carbonate. That's the side reaction. Or you could say the reaction does not go to completion as it's reversible. So any one of those would answer the question. And you'll see by going through that, we've done our calculation, we've done our percentage calculation. So that ties together the type of calculations that we would come across with this. Now, if you go to question 2, I'll guide you through it, and every now and again pause the video and try the bit, and then once you start playing again, I'll have gone over it, and then that will allow you to work through it, all right? And you'll see the question is exactly the same way that we've got the previous one, and then you'll see that the ones that follow on from that are in the same sort of pattern. So question 2 says, this question is about the amount of iron that can be produced from a certain amount of iron 3 oxide. The equation for the reaction is given below. So Fe2O3 plus 3CO gives us 2Fe plus 3CO2. So first of all, think, what's the ratios? Put them down. Okay, so the ratios, yep, using our balanced equation, 1, every one of those, 3 of these, produce 2 of those, and 3 of those. So there's our ratio, we get that from the equation. So we're going to use that somewhere further down in the calculation. So first part then says, what's the relative formula mass of Fe2O3? So Fe2O3, Fe, we're given it here in the question, we even need to use our periodic table, 56, 2 of those multiplied by 2, oxygen 16, 16 times 3, so the total is 160. So your first mark is for working that out as 160. Then use your answer in part 1. Now when they do that, there's then, here you've just done this, use it. So use your answer in part 1 to calculate the number of moles of Fe2O3 in 100 grams of the compound. Now we know N equals M, that 100 mass, over RFM, that 160. So let's put those in. 100 divided by 160 equals 0.625 mole. Okay, so then think about the next one, and again if you want to pause the video and put the answer down. How many moles of iron could be produced from 100 grams of Fe2O3? Now look at what we have here. We've got our number of moles, we've got our equation, we've just thought about the ratios, so have we think about that? Okay, so looking at our question, we're trying to work out, we know the moles of this, 0.625, we're trying to work out the moles of this, Fe, so we've got a 1 to 2 ratio. So the ratio of Fe2O3 to Fe is 1 to 2, so that means that for every 1 Fe2O3 we produce 2 Fes, so 0.625 mole of Fe2O3 will produce twice that amount of Fe, 0.625 times 2 mole of Fe, and that works out to be 1.25 moles. Okay, going on down the page, again I've got a new slide here. What mass of iron can then be produced? So you've just worked out the number of moles, turn that into a mass. Okay, so knowing that we've 1.25 mole, we know the mass of 1 mole of iron is 56. So use mass equals N times RFM. So 1.25 times 56, and that works out to be 70 grams. So up to that point, we've done our question exactly the same as we've done before. Now, this one is kind of was a slightly different one, the way it came up, this particular year it came up, because what they then asked the candidates to do was actually go back and do this calculation again, but this time what they wanted to work out was carbon monoxide. So you've worked out from 100 grams of Fe2O3 the amount of iron produced. What they then got the candidates to do is work out how much carbon monoxide was needed to react with that. Okay, so there's the equation again. So that's, again, you have that at the top of the page. I put onto this slide. So this time we're looking at this. We know our number of moles of Fe2O3. This time what we're going to try and find out is how much of this is needed. So 0.625 mole of Fe2O3, we'd worked that out earlier in the question. We know the ratio is 1 to 3. So all we do is multiply the 0.625 by 3. So it'll require 1.875 mole of CO. And then finally, the mass of that, well, we know the mass of 1 mole of CO, 12 plus 16 will be 28. So 1.875 mole, 1.875 times 28, 52.5 grams. So that's the way the questions have come up in a couple of years. And you'll see lots of other questions that continue with the book. Now, what I'd like you to do is for Wednesday, I'll put this for Wednesday, and then I'll put the solutions up on Wednesday, and then set the last couple for next Friday, and that'll finish us off with moles completely. And if you look at the next question, so it asks you to do up to question 5, which is on page 24. You'll see they follow the same way. So quite often at the start, they'll give you the formula, or the balanced formula equation. The balanced formula is an equation, so you can get your ratios from it. They'll ask you to work out the RFMs. They'll ask you to work out a number of moles. They'll then ask you to use your answer and work out masses. So you'll have to scale across using the ratios and work out the number of moles. And sometimes we'll ask you for percentage yields and the reasons why. And then you'll see the same with question 4. Again, look at the start of this. You're asked for an RFM. You're asked to work out a number of moles. You're asked to work out the mass. Use your equation, scale it across, use your ratio, and then work out your mass. And then you'll see question 5, same thing. You've got RFMs. You've got a number of moles. Scale across, work out masses, and then you're asked for a percentage yield there as well. So hopefully you'll see the rest of them are done in a similar way. So have we go at those, and let me see those by next Wednesday.